Okay, me. Hey guys, welcome to my YouTube channel Pharmacy with Preeti. So today we are going to cover the topic called X-ray diffraction. It is one of the important topic in advanced instrumentation technique. So in under this topic we are going to cover the definition of X-ray, followed by the working and the principle involved in it and the Bragg's equation. So let's begin. So starting with the definition, the X-rays are electromagnetic radiations with a short wavelength of 0.01 to 2.5 nanometer and a high energy developed by the German physicist Wilhelm Röntgen in the year 1895. So these X-rays are nothing but it is a part of electromagnetic spectra. We know the electromagnetic spectra, right? So in that spectra it comprises of various lights, that is UV, visible, radio waves, microwaves, X-rays. So X-rays are high energy waves, and its a wavelength is around 0.01 to 2.5 nanometer. So this X-ray was first discovered by the German physicist called Wilhelm Röntgen in the year 1895. Now we will see the working of it. So these X-rays are produced by an instrument called as cathode ray tube, also called as electron beam source. It is simply a chamber which is evacuated from inside and contains a cathode and the anode, which are present at the ends of the chamber. So at the extreme left of the diagram there is a cathode, and an extreme right there is a anode. Now this cathode is made up of a tungsten material, and the anode is also called as a target metal. So your anode is layered with a target metal such as molybdenum and silver. Now this cathode is attached to the electric source. So when the current is allowed to flow through the tungsten filament, that is the cathode, it gets heated and it emits electrons. Now these electrons will be attracted towards the anode, since anode carries a positive charge. Now in order to accelerate these electrons with a high speed onto the surface of the anode is applied with a high potential, because of which the positivity of the anode is increased and the electrons will now accelerate at a very high speed towards the anode. Now because of this high speed, the electrons get striked, or it gets bombarded onto the surface of the anode. Upon bombardment there is a emission of radiations called as X-ray radiations. Now we will see in detail how these X-ray radiations are being generated under principle. So in principle there are two types of X-rays are produced basically, that is continuous spectra, also called as continuum spectra, and the line spectra. So here on the right hand side it depicts the picture. We will see in detail, starting with the continuous spectra. Here the main principle involved under the continuum spectra is that the X-rays are produced due to the rapid deacceleration of the electrons by the target metal. Now what is the meaning of deacceleration? We know the meaning of acceleration. Acceleration means moving with a high velocity. Deacceleration means something which is resisting the acceleration is deacceleration. So here the electrons which are being moving with a high velocity, high acceleration, it suddenly gets reduced. The acceleration gets reduced. Therefore the name here is deacceleration of electron takes place by the target metal. So how is it happens? Let's see. So when these electrons which are being generated by the cathode, we have seen in the working, So when these electrons which is generated by the cathode, that is the tungsten filament, it gets attracted towards the anode. Okay, and these electrons are moving with a high velocity. We know that because the anode is supplied with a potential, because of which the electrons gets accelerated. Now when these fast moving electrons bombards, upon bombardment, now this anode contains a target metals, and metals consist of atoms. Numerous atoms are present. Upon striking the electrons, these electrons gets penetrated deep inside these atoms, and it moves towards the nucleus. It gets attracted towards the nucleus because electrons being negatively charged, protons or the nucleus being positively charged, so it gets attracted towards the nucleus, and therefore the electrons undergo slight deflection. Because of such deflection, the speed of the electrons gets reduced, and hence the name here is deceleration of electrons takes place. And upon deflection, as soon as the electrons gets deflected, the energy is lost in the form of X-ray radiations. And at the start of deflection, here the less energy is produced. As the electrons are deflecting more and more, the large amount of energy is being produced, or the large wavelength of radiations, X-ray radiations are produced. So here slowly the X-ray radiations are rising, right? So it is a continuous, there is a continuous spectra are produced. So in the previous diagram we can see it represents, the graph representing the continuous spectra. There is a continuous spectra, and this continuous spectra has a wide wavelength. Okay, so like consider, for example, from like it has a wide wavelength. Next is line spectra. These line spectra is also called as characteristic spectra. Why so? Because these target metals, or the anodes, are coated with the target metals, specific target metals, such as most probably the molybdenum is used as a target, and because of the use of the molybdenum, it produces a characteristic spectra. Like at a specific wavelength, it will produce a spectra, not a wide range, unlike a continuous spectra. So here what happens, similar thing happens, that is when the electrons are being generated by the tungsten filament, it accelerates towards the target metal, right, that is anode. And we know that the atoms consist of various shells, K, L, M and N. Okay, we have studied in lower standards where these atoms consist of 4 shells, K, L, M and N. Now when these electrons, those electrons which are having a sufficient kinetic energy, meaning those electrons which are moving with a high velocity, it has a it penetrates into the atoms. Okay, it penetrates deep inside the atoms, and those electrons which are having high or sufficient kinetic energy, that it can able to knock out the electrons of the innermost shell. Let's say consider here K shell. If it knockouts the electrons of the K shell, the incoming electrons, removing the electrons from the K shell, this creates a void space in K shell, right? Now this void space will be occupied by the outermost orbital ka electrons. So the L shell will try to donate, or the M shell will try to donate its electron towards the K shell, and this transfer of electrons will result in the generation of radiations called as X-ray radiations, and this X-ray radiations are referred to as K series because the electrons are being donated to the K shell, and hence it is referred to as K series. It can also take place in L series, M series and N series. It depends upon the kinetic energy of the electrons which are having or which are being emitted by the cathode. Starting with the Bragg's equation. Now let's define the X-ray crystallography. X-ray crystallography is a branch of science which deals with the study of structures and properties. So here we deal with the study of structure, the crystal structure and its properties. The X-ray diffraction is explained by Bragg's equation, and therefore we say that if the Bragg's equation is satisfied, then only the X-ray diffraction will happen, otherwise not. So XRD, that is X-ray diffraction, is a non-destructive method which is useful for identification of the structure, its arrangement in space. Here non-destructive refers to it doesn't modify the crystal structure. Without changing the structure or without doing any processing to the crystal, we can be able to find its structure, its internal molecular structure. Now when the sample is placed between the cathode ray tube and the photographic plates in the sample holder. Okay, so we have seen the working of a cathode ray tube, right? From the cathode ray tube the X-ray will be generated, and at the center the sample, that is the crystal sample, is placed, and on the right hand side the photographic plates where the diffraction pattern will be generated, and which will be detected by the detector. When the X-rays are emitted by the cathode ray tube, it is going to be absorbed by the atoms of the crystal. Further, it is going to scatter the reflected light from the atoms, and this is nothing but the diffraction, and the pattern will be generated on the photographic plates. These X-rays are the high energy light with a repeating period called as wavelength, right? So we know that these X-ray are nothing but the radiations or light, and the light is represented by the waves in the form of waves. Okay, so and these waves can be measured in terms of wavelength. If the wavelength of X-rays is similar to the distance between the atoms in the crystals, then the interference will occur, meaning here the X-ray radiations which are being coming or which are approaching towards the crystal, the distance between the distance in the wavelength of the X-rays should be similar to the reflected light emitted from the crystals, then only the interference will occur. If the wavelength of the incident radiations and the scattered radiations are same, then constructive interference will occur. So here in the picture we can see that the on the topmost figure here, the uppermost wave indicates the incident waves, and the lowermost waves indicates the reflected waves which are being emitted by the crystal. Both are in same phase, right? Both are in same phase, so the resultant waves are results in constructive interference, which is detected by the detector. However, if the incident, on the right hand side, see the diagram, if the incident rays and the reflected rays, here both of them, they are not in the same phase, and therefore the resultant interference will be a destructive interference which will not be detected by the detector. Right, in detail we will see in the Bragg's law, in the Bragg's equation. Let's continue further. In the crystal, the repeating arrangement of the atoms forms a distinct planes, and these planes are separated by the well-defined distance known as interplanar distance. This will be understood well in the Bragg's equation. We will discuss further. When the X-rays falls onto the topmost layer, the incident and the scattered light travels the same distance. But when the X-rays falls onto the innermost layer, both the incident and the scattered light need to travel some extra distances, and these extra distances are referred to as path difference. As the X-ray falls to the deeper layers of the crystals, the path difference will keep on increasing. So in order to get a constructive interference, why we need a constructive interference? In order to detect the structure of the crystal. Therefore we need a constructive interference, because the detector can only detect the constructive interference and not the destructive interference. So in order to detect the constructive interference, the path difference should be a whole number. Okay, right? So this explanation is related to the Bragg's equation. We will discuss. So look at the picture, look at the diagram. Here this triangle represents a crystal, right? And the points you can see, it represents a atoms. Now, and it is divided into planes. We can see 3 planes, right? And the distance between the planes are referred to as interplanar distance. Previously we have defined the distance between the 2 planes, that is represented by D, that is referred to as interplanar distance. Now when this is L represents the incident radiations, when the LM it represents incident radiations. Okay, so when this incident radiations from the cathode ray tube is going to generate the X-rays, right? So when these X-rays falls onto the topmost layer, this is my top layer, this is my second plane, this is my third plane, and these 2 planes are the distance between the 2 planes are referred to as interplanar distance, which is represented by letter D, right? You can see. Now when these X-rays falls onto the topmost plane, topmost layer, the distance between the incident and the reflected ray is same, and hence it will result, they are in same phase, and it will result in constructive interference. However, when the radiations, incident radiations falls into the deeper planes, into the deeper layers of the planes, now it may or may not be in the same phase. The incident and the reflected ray, it may or may not be in the same phase. Why so? Because here we can see that both these radiations need to travel some extra distance, that is AP and CP. These are the extra distances, right? So they need to travel some extra distances, AP and CP. Okay, so till L to O and till O to this point, the distance is same. However, in case of this, it need to travel these extra distances, and these extra distances is nothing but the path difference. So ideally the path difference should be the whole number, so that it result in constructive interference. Okay, similarly here also, this incident light, when it falls to the deeper layer, again it needs to travel some more extra distance, b to r and r to d. Okay, some more extra distance, that is path difference. So let's consider this. Let's see the equation of Bragg's law. Here the incident and the reflected angle is referred to as theta. Okay, this is theta. Incident and the reflected angle is referred to as theta. So in triangle AOP, now here, because of vertically opposite angle, if this angle is theta, this angle would also be theta, right? So in triangle AOP, apply sine theta. Sine theta is equal to opposite upon hypotenuse. So the opposite of theta is AP and the hypotenuse is OP. And we know that OP is nothing but interplanar distance, that is D, which is represented by D, that is AP upon D. It will be AP upon D. Now we will arrange this as AP equal to D sine theta. Similarly, we will carry out for triangle COP. So in triangle COP, same, sine theta is opposite upon hypotenuse. So opposite would be CP and hypotenuse would be OP upon OP. And OP is again interplanar distance D. So upon rearranging, we will get CP is equals to D sine theta. And now this AP plus CP is nothing but the path difference, right? So AP plus CP, now we will add both these equation. AP is D sine theta, so we have written here D sine theta plus CP, plus CP is also D sine theta, so D sine theta. Now D sine theta plus D sine theta will be 2D sine theta. Since AP plus CP is a multiples of lambda, AP plus CP is a multiples of lambda, meaning lambda is wavelength. So consider if here there is one wavelength, so ideally CP should also be one wavelength only. Then only the constructive interference will occur. If AP is two wavelength, then CP should also be two wavelength. Then only it will result in constructive interference. So AP plus CP is considered to be as multiples of lambda, and so AP plus CP we will write it as lambda. So it would be lambda is equals to 2D sine theta, and upon rearranging we will get sine theta equal to n lambda upon 2D, where theta is the angle of incidence, right? Lambda is wavelength, D is the path difference, and n is integer. I hope you understand the Bragg's equation. Thank you.